So now we're going to take a closer look at our trigonometric function graphs, primarily sine, cosine, and tangent, but we'll look at the other three as well. And what we're also going to be interested in doing is what we did with general functions back in the fall, and that is to translate left and right, to vertically stretch, vertically shrink, to horizontally stretch, to horizontally shrink these functions. So we have our basic sine function, which you guys have kept track of now for a couple weeks. It's periodic, meaning its fundamental period is 2 pi. It repeats itself every 2 pi units. It has an amplitude of 1, because remember, the amplitude of a periodic function is the maximum minus the minimum divided by 2. So 1 minus 1 is 2. 2 divided by 2 is 1. Our amplitude is from arguably a midline between the max and min up to the max or down to the min, and our amplitude is that distance either from that midline up to the max or from the midline down to the min. So how can we fiddle around with this graph? Well, let's consider the following. So let's suppose we look at 2 sine x plus 3. What I'm going to do first is obviously take my sine x values, y values, multiply them by 2. That's going to be a vertical stretch by a factor of 2, and then I'm going to move everything up 3 units. So if here's my original sine curve out to 2 pi, what I'm going to do first is everything will get stretched by a factor of 2. So then I'm going to come up here to 2, and I'm going to go down to negative 2 down here. And then I'm going to take everything and move it up 3 units. So that 0, 0 is now going to come up to, if I move it up 3 units, to 0, 3. I'm here at pi over 2, 2. So if I move that 2 up 3 units, it's going to move up to 5. So pi over 2, 5. This 0, 0 down here is going to go up to 0, 3. Over here I had 3 pi over 2, negative 2. If I move up 3 units, that's going to come up to 1. And then I'm back up here to up 3 units from 0 takes me up to 0. So again, I'm just going to take that whole, the whole vertically stretched curve down here and move it up 3. So how about sine of 3x? We remember if we placed x with 3x, that's going to be a horizontal shrink by a factor of 3. So think about it. If we did a full period, if sine x takes on a full period out from 0 to 2 pi, for sine of 3x, it's going to be a horizontal shrink by a factor of 1/3. So take that 2 pi length, and instead of having the period be 2 pi, it's got to be horizontally shrunk by a factor of 1/3. So now I'll get a whole period in from 0 to 2/3, 2 pi over 3, which would be 2/3 of pi. So from 0 out to 2/3 of pi, I'll get a full period. Note my amplitude hasn't changed at all. And how about we consider sine of a quarter x? Well, if we replace x with a quarter x, we remember that's a horizontal stretch by a factor of 4. So if originally our sine function, sine x, has a period of 2 pi, now if we vertically stretch by a factor of 4, instead of getting a period done in 2 pi units, I'm going to take 4 times that, or 8 pi units, to get a period in. And that should make sense a little to you, because consider, for example, if I put 0 in for x here, sine of 0 is still 0. I'm heading out, x becomes greater and greater. In order to get a full period of the sine function done, I've got to make this equal to 2 pi. So what's going to make this equal to 2 pi? Well, I'd have to put an 8 pi in for x, because 8 pi over 4 is 2 pi. Put an 8 pi in here. 8 pi over 4 is 2 pi. Sine of 2 pi is going to be 0 again. So from 0 to 8 pi, I get my complete period done. And as we can see, from 0 to 2 pi, relative to 0 to 8 pi, that's a horizontal stretch by a factor of 4. How about these two? We have replaced x with x minus pi over 4. That's going to move our sine function left or right pi over 4 units. Replace with x minus right pi over 4 units. So if we had originally our sine function here, we're going to slide it, and this is pi over 2, it's going to slide over left pi over 2 units. How about the next one? Negative 3 times sine of pi x. Well, the negative is simply going to flip, we know, the function over the x-axis. The 3 is going to be a vertical stretch by a factor of 3. So I know I'm going to take my sine function, and it's going to be vertically stretched by a factor of 3, but flipped over that y-axis. So I know I'm looking at 3 and negative 3. The question is, what's this replacing x with pi x going to do? Well, same thing. It's going to be pi is greater than 1, so I know it's going to be a horizontal shrink by a factor of 1 over pi. So how can I see what my new period is? Well, one way, again, is to look at, if I put 0 in here for x, sine of 0 times pi is still sine of 0, so at 0 I'm still here. What's going to happen, what would I need to put in for x to get this to be a 2 pi? And the answer is I'd have to go out to 2. If x were 2, I then would be out to 2 times pi, or sine of 2 pi. So indeed, my period here for this function is going to be 2, and you'll note that if we say it's a horizontal shrink by a factor of pi, 1 over pi, that's 2 pi divided by pi, which is 2. So I can view and figure out what my period is for a sine and cosine function by taking the fundamental period of 2 pi and dividing by whatever constant I have that's different from 1 in front of x. Let's take another look at an example. So note here, if we have something like y equals sine of 3 pi x, our period normally is 2 pi. 3 pi is a number bigger than 1, so I got a horizontal shrink. It's a shrink by a factor of 1 over 3 pi. So take the 2 pi, divide by 3 pi, that gives you 2/3. My period then is going to be 2/3 for this function. Note again, if I put in 0 for x, sine of 0 is 0. If I put in 2/3 for x, 3 pi times 2/3 is 2 pi. So going out from 0 to 2/3 is equivalent to going from sine of 0 to sine of 2 pi. That gets me my full period. No change here with our horizontal shrink, no change in maximum or minimum values, no change in our amplitude. So our tan graph, we remember, has asymptotes with multiples of pi over 2. Our tan graph, when we thought it through, is a curve that rises from left to right. It's a snake. Tangent can take on any value, so the range of our tangent function is all real numbers. Our domain, however, we're not permitted to put in any multiple of pi over 2, because we remember that the tangent is the y over the x, and at multiples of pi over 2, my x-coordinate would be 0 on the terminal side of the angle, and anything over 0 is undefined, and indeed that's why I get my asymptotes. So from that basic tan graph, we can also stretch, shrink, do a whole bunch of stuff. Note that for the tan graph, we would not say that it has any amplitude. There's no amplitude because it doesn't have any maximum or minimum value. Amplitude implies that I'm varying regularly between a maximum and minimum value periodically. And while the tangent function is periodic, we say that there's no amplitude because there's no max minus min divided by 2. So suppose we have our regular sine graph, which is dotted here above, and we want to look at the cosecant graph. We know that the cosecant is the reciprocal, by definition, of the sine. In other words, the reciprocal of sine x is cosecant x, because we note that the sine is y over r, whereas cosecant is defined to be r over y. So if I want to look at the reciprocal of the y values here, in this case, my reciprocals of zeros are undefined, and that's indeed why I get my asymptotes where I do for my cosecant graph. So where the sine function is 0, that gives me asymptotes. And then I simply want to say, hey, what's the What's the reciprocal of my y values here? Well, the reciprocal of 1 is 1. The reciprocal of -1 is -1. Reciprocal of -1 is -1. Reciprocal of 1 is 1. So I know that the sine and the cosecant graph are going to share a set of points. And again, reciprocal of a very small positive number, for example, reciprocals of small positive numbers, very large positive numbers, and reciprocals of very large negative numbers. Reciprocals of very large negative numbers, being negative though, are going to be very small negative numbers. And if I follow that pattern out in each little subsection here that the asymptotes divide our graph into, I wind up getting my cosecant graph. And once I see the cosecant graph, certainly I can, if I do this by pencil, I simply erase. I can erase my sine graph and just leave your cosecant. Note that the cosecant graph also is periodic. It repeats every 2 pi, and I can see that kind of as a going up, a going down piece, and then it's going to repeat. Up and down, repeats, up, down, repeats, and my period indeed is 2 pi. Similarly, you can come up with the secant graph from the cosine graph, and certainly from the tangent graph you can and should be able to think through and come up with the cotan graph and confirm that cotan graph with your calculator. By definition, we're going to say that the frequency of a periodic curve is going to be the reciprocal of its period. And I'll illustrate that as follows. Let's suppose we've got a periodic curve here that in 1 unit it repeats 4 times. My period then we know is 1/4 if it repeats 4 times in 1 unit. Period is 1/4. The frequency would be the reciprocal of 1/4, which is 4. So in other words, the frequency is in 1 unit on my x-axis scale. In 1 unit, how many times does an object repeat itself? Does the periodic object repeat itself? Now, does the frequency always have to be bigger than 4? And the answer is no. If I have, say, something that's periodic with a period of 2, by our definition we just talked about, the frequency is the reciprocal of the period, so the frequency would be 1/2, which means that for every 1 unit, how many times does our period happen? And the answer is in 1 unit. Well, in 1 unit, I've only come halfway. I've only done 1/2 of my full period, so my frequency is 1/2. One more example. Periodic, and over 1 unit, I've had my period repeat 8 times, so my period is 1/8, and my frequency is the reciprocal of that, which is 8.